All right, line A6, learning task 7. This is going to be the last of these circuit diagrams that we're going to go through out of this learning task. And this one is going to go and be for an AC motor. And it's going to be a triac motor starting switch. Now I'm going to go and first of all tell you it's going to be a little bit advanced for what we have covered so far because we haven't covered these motors themselves, how they actually go and operate and what makes them special. So some of this you're just going to have to take on, just the fact that I'm telling you this as to how these things go and operate. Later on, when we go into single-phase motors, we're going to come back to this diagram because it just makes sense for us to go through then, having known a little bit more about the actual motor itself that's going to be inside of there. But ultimately, for now, we're just going to break the motor into three parts. We're going to have a run winding, we're going to have a start winding, and we're going to go and have a rotor. And these are all going to go and be electromagnetically linked. Current that is going to go and travel through the start winding and the run winding, we'll just stick current through these directions here right now, are going to go and create magnetic fields. Those magnetic fields are then going to go and interact with the rotor, and then as they interact with the rotor, they're going to start this thing rotating. And what you see up top over here is that we're going to go and have one winding that is just simply going to be a winding, also known as an inductor. So we know that my voltage in my current is going to be lagging. And then the other section of the motor, check it out, this capacitor is also tied into this motor, is going to go and have an inductor and a capacitor inside of it. So we are going to go and have both, Eli and ICE, which altogether means that if I've got a capacitor and an inductor together versus just an inductor, I'm going to go have two separate phase angles. So one winding's going to have a phase angle, the other one's going to have a separate phase angle. And this is just the way that these motors operates. What gets them going is the fact that we are going to go and have some sort of a delay on one winding compared to the other, so that one is going to peak first, the rotor is going to start turning in that direction, then the next one's going to peak, and then after that it just kind of chases it around and around inside of a circle. That's what happens. Initially, what is also going to go and happen inside of here is that there's going to go and be a large amount of current that is going to go and happen because initially we're not going to get a lot of counter EMF. So when we first turn this on, we're going to go and get a massive slug of current that's going to start up. You should be familiar with the fact that when you start a motor, we get inrush current, as we call it, which is typically going to be a value up to about 300% or 3 times the regular current amount. That current, as we turn this thing on, so we have a switch somewhere out here in the system. We'll break both lines over here because I don't know which is the neutral. But we're going to go and switch this thing. As we switch this thing and close these in, we're going to go and get this inrush that's going to go and happen. We'll make this instantaneously negative. We'll make this instantaneously positive over here. As that happens, we're going to go and get lots of current that is going to go and travel through here. I'm going to draw 2 parallel arrows to go and symbolize the fact that we've got a lot of current. All of that current going through this resistor is going to go and give me a value of voltage. V is equal to I times R. So if I've got a lot of current going through my initial inrush, what do I know about the voltage? Well, if there's lots of current over here, therefore there would be lots of voltage that would be dropped across there as well. It's a relatively small ohmic value, 0.04 ohms that they have for this one over here, which means that a lot of current is only going to give a small rise in voltage, but that small rise in voltage is what's going to go and trigger this over here. If you take a look at this, we see that there is a gate that's attached over here to my triac going across this resistor. So as long as I'm developing a voltage across this resistor, I'm going to go and have potential difference, and this triac is going to go and turn on. So we start this motor, we provide power, we get all of this inrush. Because we get that inrush, we're going to go and have voltage at the gate, which means that we are also going to go and have current that is going to go and flow through here. Okay, so we're going to go and have a lot of current that is going to go and flow through that section because really we're bypassing this over here, which is going to go and be a capacitor and a resistor together that is altogether going to go and provide us with a Z, an impedance that we're going to go and have across there. So we're bypassing that because this triac acts like a closed switch that we are going to go and have. So our AC is going to go and run through here. We're going to go and have practically full voltage. There'll be a little drop over top of this, but practically full voltage that's going to happen over top of this start winding. And this capacitor that we see inside of the dotted line, right, is a part of that start winding. The motor is going to start to turn. As the motor starts to turn, the rotor is going to go and start to build up some counter EMFs, and what we start to see happening is we start to see the current is going to be dropping. Now we're still going to have current running through here, but the current that is going through my run windings over here is now going to drop. And as it drops, that means that the resultant current that's going through here has also dropped, which means that if this I has now gone down, that would mean that this voltage over here is also going to go down. And as that voltage drops, it is now no longer going to go and gate that SCR. So on the next AC alternation, as we pass that 0, our neutral plane over there, we are going to go and lose holding current, and this is going to go and shut off. What happens then is that we still do have a current path through, but it's going through this resistor and this capacitor that are going to go and be over here. Altogether, the inductance of the start winding, the resistance of these, copper of that start winding, as well as this resistor here, and these two capacitors that we're going to go and place in series like that now, is going to go and give us an overall large Z. And because we're going to go and have a very overall large Z, we're going to go and have a small current, a small start winding current that is still going to go through. It's going to be a tiny amount of current, this green line that we're going to see there through there, and it's going to be continuous. But it's great because it's a solid state motor control that we have at this point. When we cover start and run windings or single phase motors later on, we're going to find out that the other way for us to go and turn these motors, start them up, is that we're going to go and have a special type of switch. So if I just go and, who knows if my way will work here today, but if I white that out over there, what we usually have off of these is that this is going to be my line, and then this over here is going to go through a 0-speed switch, which is going to go and be this one special kind of switch that, you know, whenever it's turning, it's going to go and make contact. And what happens is that as this motor gets higher and higher in its centrifugal, or in its rotation, centrifugal motion is going to go and open this switch. So as the motor comes up to speed, this switch opens under normal operation for one of these motors, and then it shuts off so that we have no more current going through that start winding. We're only running current through the run winding. The start winding is simply in the motor during that startup process. The problem with that is that this is mechanical. And anytime that you're working with motors, you're generally working inside of somewhat of a, you know, industrial type of an application in a lot of cases. And anything that's mechanical gets gummed up. There's always going to go and be, you know, dust that's going to go and build up. The fact that we've got charge, electrical current flowing through there means that we're going to attract dust, and it's just going to go and, you know, cause issues. If you've ever worked in heavy industry, you know everything gets gummed up. So anything mechanical that has to rely on spring action and centrifugal force needs to then be maintained. This section over here, most common issue. When I was working in the field and when I was teching for a while as well, most common issue with single phase motors that aren't working is that that switch is screwed up. And usually all I would have to do is go and, you know, open it up, replace that centrifugal switch, and this thing would be good as new. Once again, you're going to get another, you know, 10 years of life out of it. But it can be a bit of an issue, so we can go and ignore all that by using this solid state. In the solid state one, we don't completely disconnect the start winding. Normally I'm going to go and have start current that's going to go through here, which is going to be a large value of current that's going to go through there. But as soon as I am no longer gating the start winding, once I get up to speed and this run winding current has dropped away, then this shuts off through the main triac, but I will always still have a tiny bit of current that's going through here. It's not going to be enough that it's going to go and hurt the motor. It's going to make it a slight bit more inefficient, but it's going to be fine as well. The good thing is that, you know, you've gone and lost that centrifugal switch. You don't have to go and maintain that. I do want to point out one other thing inside of here as well. That is that this is a specialized controller built for a specialized motor. I cannot just take these values that are inside of here and apply them to any motor. In other words, you can't get a standard standalone electronic, you know, AC motor starter that's for single phase motors. You do need to go and build it specific to that. So you would have to know what the start winding is composed of, the resistance, the capacitance, as well as what we're still missing inside of here, the inductance in henries. So you have to know that. You would also need to know this, the L, the inductance in henries, as well as the resistance of your run winding. And then from that, you could then go and calculate all the rest of these values. This is going to go and be dependent upon my inrush current through this motor and whatever I need for my voltage, because I need to go and develop however many volts to go and gate this triac based upon that actual triac. So I'm going to start with looking at what am I going to go and have for my run currents. I want whatever's traveling through here to be just a bit low, so it's not going to be gating this thing during run current. and that way I'm guaranteed to pick it up on my start. So I start by sizing that, then I go and carry that over to this triac, then I got to build the rest of this around. 99% of the cases, it's not going to be you that's going to go and build this. It is just going to be a component that is going to be bought from the manufacturer. The manufacturer is going to say, hey, you want to buy this model motor, then you want to also go and buy this model of starter that is going to be compliant with that same motor. We'll come back to this thing later on when we do cover motors. For now, just, that's the basic operation of it. All we're looking at is that we get lots of current through here, which is giving us voltage, gating this triac over here. Don't worry so much about this section, the little snubber circuit over here. This is just because when we have a rotor in there, the rotor acts like a rotating transformer, and otherwise we're going to be getting spikes of voltage across this inductor that's going to be picking up that can cause damage. So we just give it a complete path all the way through. Okay, that's it for learning task 7, which has got a lot of cool but complicated circuits inside of it. Cheers.